Data structures and algorithms. Data structures. Data is a broad term that refers to all types of information, down to the most basic numbers and strings. In the simple but classic Hello World program like this, the string Hello World is a piece of data. So this Hello World is a data, a string. In fact, even the most complex pieces of data usually break down into a bunch of numbers and strings. So these are the data in the data structure. Um, in the most basic and simplest form, the data structure and algorithm, which is considered one of the hardest concept to grasp in computer science, is just a numbers and strings. So that's for the data. Data structures refer to how data is organized. The program below has three pieces of data, outputting three strings to make one coherent message. Hello, how are you today? So this has three pieces of data, and then using console to output a coherent message. The array, the foundational data structure. So what is the most basic data structure? So how do we or what's the fundamental structure of this data? It's actually an array. Array is a list of data elements. If you're looking at the source code for application that allows users to create and use shopping list for the grocery store, you might find code like this. Array equal apples, bananas, cucumbers, dates, elderberries. This array happens to contain 5 strings, each representing something that I might buy at the supermarket. So you've got to try elderberries. So this array happens to have 5 strings, each representing, and this string in each array is actually an index, but it starts with 0 because that's the format for the data structure. So any data structure that we will gonna use usually have a 0. So you could think of that as most common in data structure, especially for the interviews. The most common data structure that you're gonna use has an index that start with 0. So how do we measure speed in data structure? When we measure how fast an operation is, we do not refer to how fast the operation takes in terms of pure time, but instead in how many steps it takes. So the reason why we need to measure the steps is because the time could vary from case to case, from computer to computer, from user to user, from memory to memory, from CPU to CPU. So there's a host of environmental and different complex factor that affects it, but we're only concerned with how our code performs, so we're measuring the steps instead of time. We do this because we can never say definitely that any operation takes say 5 seconds. While a piece of code may take 5 seconds on a particular computer, that same piece of code may take longer on an older phone. Reading. So this is the fundamental operation. So remember, in JavaScript, this is one of the first operations. The operations in JavaScript are addition, subtraction, multiplication, division. Those are the fundamental operation. While here, for data structures and algorithms, the first fundamental operation is reading, which look up what value is contained at a particular index inside the array. So this assume that you already know the index, because for computer it's easy to find the value uh, if you already have the index. So unlike searching, which we will discuss later, it's harder for the computer. It takes a lot of cognitive load or compute power to do that. But instead, in how many, sorry, which look up what value is contained at a particular index inside the array A. A computer can read from an array in just one step. So the step needed for the computer or memory to find the value, if it already knows the index, is just one step. This is because the computer has the ability to immediately access any particular index in the array and peer inside. So assuming you have an access to, the computer usually have one step, because it's just the way it works. So you could think of this as a memory. So let's say you already know the index, or your application know the index, or the computer know the index. So how would your computer know the index? Your application will be designed to know that index. So for example, CPU copy your application from disk to memory, and now it's currently running. So the speed of that for reading would be fast, because it only took took it one step for reading that. So for opening, reading is like getting a value of something on an array of a variable. So that could be like when you open an application, when you read a document, that is type of reading. In our example of apples, bananas, cucumbers, dates, elderberries, if we look up index 2, the computer would jump right to index 2 and report that it contains the cucumbers. So here is the cucumbers, because it starts from 0, 1, 2. So it already know. How is the computer able to look up an array's index in just one step? Let's see. A computer's memory can be viewed as a giant collection of cells. In the following diagram, you can see a grid of cells in which some are empty and some contains bits. So here, as you can see, some are empty here. So how our CPU are able to present us the index of an array using its how are the CPU are able, or computer are able to present us the value of the index. In just one step, it's so fast. So here, as you can see, a memory is just a giant of collection of cells. So this is actually the applications that we see. Like this OneNote, it stores on the memory of my computer right now. So it's a giant collection of cells. So in the following diagram, you can see a grid of cells. So you can think of this as a grid of cells as well, in which some are empty and some contain bits for the memory. Some are empty and some contain bits. So searching, another operation, in a sense, it's the inverse of reading. Reading means providing the computer an index and asking it to return the value contained there. Searching, on the other hand, means providing the computer a value and asking it to return the index of that value's location. So now you have a value. For example, when you're searching something in Google Chrome, you have the value. So the computer now must reverse engineer that from value to find the index that contain that value. It used an algorithm uh, to search that. While these two operations sound familiar, there's a world of difference between them when it comes to efficiency. Reading from an index is fast, since a computer can jump immediately to any index and discover the value contained there. So the reason for that one step for computer is because it has a huge memory. So it could remember, for example, on your application, when the CPU copy it to memory, those your memory now has this huge piece of indexes that the CPU copy from your disk to memory. Now that huge of indexes will be turned on while the computer is turned on or the memory is turned on. So let's say you have the index 1016. Since that is powered on and the computer is already running, it will immediately allow you to get the value of that as long as your memory supports remembering, huge, which is most cases today, like 8 gig to 16 gig memory could hold like a million pieces of data. So the memory will just take one step because it's already powered on. It is designed to uh, simultaneously operate those huge pieces of data so that it could take just one step. However, for searching, it will take a little bit it will take longer. Insertion. So this is another fundamental operations in data structure. The efficiency of inserting a new piece of data into an array depends on where within the array you're inserting it. Let's say we want to add figs to the end of our shopping list. Such as an insertion takes just one step. So for a computer data structure, the usual way or the way they one of their characteristics is that it's easy for them to insert at the end. So that's the usual characteristics. But later we will discover in the subsequent videos is that some data structure actually are more efficient in adding at the beginning, but you can only choose either at the end or at the beginning. As of now, that's the current state of our hardware, and that's how memory works. That's the fundamental characteristics of this. You cannot add at the middle or at the second, though there's some techniques to do that, but the basics are just inserting at the end and inserting at the beginning. This is true due to another fact about computers. When allocating an array, the computer always keeps track of the array's length. So the reason for this is because when you allocate an array, for example, you create a code or a piece of software or for an application that asks a computer to create an array like this, which we will create in the later subsequent videos. When you create that array, the computer will track its length on how many pieces of index it has and the corresponding value. So when we couple this with the fact that the computer also knows at which memory address the array begins, computing the memory address of the last item of the array is a cinch. So when you know the length, and the computer will also know the memory which memory address, because it knows the index. Computing the memory address of the last item of the address is a cinch. If the array begins at memory address 1010 and is of length 5, that means its final memory address is 1014. So another fact about this is that it uh, since it tracks these memory addresses, and it allocates this array depending on which application you open first. For example, you open this OneNote. This will, for example, consume the 1010 to 1015. And then another application, you open it, for example, I open share it, then it will take 1015, for example, to 10120. So the computer immediately tracks that. That's why it's easy for it to insert. So insert an item beyond that would mean adding to the next memory address, which is 1015. Deletion, so this is another fundamental operation in data structure. Deletion from an array is the process of eliminating the value at a particular index. So let's return to our original example array and delete the value at index 2. In our example, this value is cucumbers. So while the actual deletion of cucumbers, I don't know how to pronounce it, cucumbers technically took just one step. We now have a problem. We have an empty cell sitting smack in the middle of our array. An array isn't effective when there are gaps in the middle of it. So to resolve this issue, we need to shift dates and elderberries to the left. This means our deletion process requires additional step. Step 2, we shift dates. So it's kind of like swap, because you're swapping the space here and then swapping the space again here, but we call this shift. So deletion take 2 steps, so it's not one step like an insertion. And reading, so as we will see, searching actually is not a one step. There is another way to measure its efficiency. And again, our main point here is that this is the way for us to measure the efficiency of our code through operations, through steps. Okay, from steps to operation, what operation it does, because the operation it does will determine how many steps it will take. So sets, how a single rule can affect efficiency. Sets, sets is another variation of array. Now we're getting to the more and more nuanced type of data structure, which is sets. Let's explore this other data structures. The set. A set is a data structure that does not allow duplicate values to be contained within it. So if you want an application that do not accept these multiple accounts, so this is the way to go. Sets are of different types, but for this discussion, I'll talk about an array-based set. This set is just like an array. It's a simple list of values. So there are different types of set. There is also an array-based type set, which just a list of values. The only difference between this set and a classic array is that the set never allows duplicate values to be inserted into it. So the only nuance between array and set array is that you cannot insert at the end of it a duplicate one which already contains in the set of value. So the computer will notice that because again, remember, the CPU or the memory keep tracks of all the index and values. For example, if you had a set ABC and tried to add another B, the computer just wouldn't allow it since a B already exists within the set. Sets are useful when you need to ensure that you don't have duplicate data. For instance, if you're creating an online phone book. Wrapping up, analyzing the number of steps an operation takes is the heart of understanding the performance of data structures. So steps and operations is at the heart of it. Steps and operation, but it begins with the step and operations. In this chapter, you've learned to use this analysis to weigh whether an array or a set might be the appropriate choice for a given application. Again, your application will be stored into memory to the computer from CPU. It copy it from the disk, the application, and then copy it to memory. So that's how it actually works. Now that you've begun to learn how to think about the time complexity of data structures, we can use the same analysis to compare competing algorithms even within the same data structure to ensure the ultimate speed and performance of our code. Now, we will now measure the algorithm. So that is the basic of data structures. Why algorithms matter? Even two data structures that seem so similar, such as the array and the set, can have very different levels of efficiency. So the data arrays that we've measured, such as the array and set, could have different steps and operations. So we could define now an efficiency as steps and operations for its efficiency. So it has a different depending on the requirements of your application, whether it needs a duplicate or not. If it needs a duplicate, the sets array are more efficient. In this chapter, we're going to discuss that even if we decide on a particular data structure, another major factor can affect the efficiency of our code, the proper selection of which algorithm to use. Although the word algorithm sounds something like sounds like something complex, it really isn't. An algorithm is simply a set of instructions for completing a task. Ordered arrays. So again, an algorithm is just a set of instructions for completing a task. So this is what most people think as programming when they think about programming, but it's just one part of programming. There's a lot of other things that they need to do. Ordered arrays. The ordered array is almost identical to the classic array we saw in the previous chapter. So it's almost the same with the classic array. So this is a more nuanced array, an ordered array. The only difference is that ordered arrays requires that the values are always kept, you guessed it, in order. That is, every time a value is added, it gets placed in the proper cell so that the values in the array remain sorted. So what does it mean? It means that the steps and the operations will be different as well. So for example, and it has a different time or steps rather, or efficiency. For example, let's take array 3, 17, 18 80, 202. Assume you want to insert the value 75 into the array. If this array were a classic array, we could insert the 75 at the end as follows. So for the classic array, we could only we would insert it at the end. However, that's not actually the case for ordered arrays because it needs to be ordered. This 75 needs to go here at the middle. Now searching an ordered array. Previously we mentioned searching as the one of the fundamental operation for data structure. Now previously we described the process of searching for a particular value within a classic array. We check each cell one at a time from left to right until we find the value we're looking for, and this was linear search. So there's for searching, it's an operation, but there is a nuance in different types of this operation. So as you can see, we get more complex, but it still came from two basic measurements, which is steps and operations. But for that operations, there's searching, and in that searching, there is a linear search. Now let's see how the linear search is different in classic and ordered array. So to achieve this, to understand searching, we need to know how is it different from ordered and classic arrays. Say we have a regular array of 17, 3, 75, 202, and 80. If we were to search for the value 22, which happens to be non-existent in this array, we would need to search each and every element because the 22 could potentially be anywhere in the array. The only time we could stop our search before we reach the array's end is if we happen to find the value we're looking for before we reach the 22. Unlike when it is ordered, we immediately knows its index. So that's the difference for ordered and classic array. For a classic array, you need to use a linear search, which is from left to right to search for a particular value, such as this 22. However, if it's already ordered, we immediately know that it is not from one of its index. So that's the difference for ordered and classic search. So the main difference is the search operation it does to complete its steps. So it has different efficiency. Now binary search. So this is another type of operation. Search operation. As a child, you play the guessing game of a guessing number, a number 1 to 100 from what the opponent are thinking, and he'll let you know your guess is higher or lower. So one of the metaphor for this binary search is the guessing game. So you know intuitively how to play this game. You wouldn't begin by guessing number 1. Instead, you'd probably start with 50, which is a smack in the middle. Why? Because selecting 50, no matter what I tell you to open, no matter whether I tell you to guess higher or lower, you would have automatically eliminated half the possible numbers. So this is kind of like the binary search. So another type of search that has more efficient steps. So for these operations, there is like for linear search, it takes these n steps. For binary search, this took like this faster steps, right? Because you're eliminating half of the possible searches. So this is the difference between this. As you can see, guys, there's a difference with the data structure, the step, and operations. So this is the three fundamental things that we need to understand here. Now, binary search versus linear search. With order arrays of a small size, the algorithm of binary search doesn't have much of an advantage over linear search. So, in that operations that we use to measure the efficiency of data structure, those operations is actually an algorithm itself. As you can see, it's different from JavaScript in a way that the operations there are addition, multiplication, subtraction, and division. Those operations, those four fundamental operations, are equivalent to like reading, insertion, deleting, shifting, swapping, and comparison in data structure. However, within those operations, it is actually algorithms. And algorithms consist of this complex, a set of instruction for completing a task, just like an addition, subtraction, multiplication, and division does. But for this algorithms and basic operations, there's a nuance in these operations. And for different languages, there is actually an actual name uh, or uh, there is a name like that provides those entire operations. Okay, so we call from right now we call the algorithm as an operation. So as you can see, with an array containing 100 values, here are the maximum number of steps each type of search would take. So how do we measure steps from those operations and algorithms? Sorry about that. How do we measure steps from those algorithms? So we measure steps through maximum or the worst case scenario, which we're gonna discuss further later. So we find the worst case usually, and then we find the medium, the average case, or the average case, and the best case. So those are the things that the operation could take in those different cases. So these operations like the addition, subtraction, and multiplication, like the basic math operation, has been more sophisticated, but it added a lot of compute power, because then we just need to call these operations for us to determine these steps. We just need to find the right algorithm in the right case. So here, with linear search, if the value we're searching for is in the final cell or is greater than the value in the final cell, we have to inspect each and every element. So let's say we're trying to find a value that happens to be at the end of the cell. Then we need to inspect each element, which is will take the how many elements on the array. Let's say there you have this index of 99, which is 100, because it starts from 0. It will also take that 100 step. So when we use binary research, however, it only takes 7 steps, as you can see here. When we use binary search, however, each guess we make elimination half of the possible cells we'd have to search. So we eliminate half of the cell that we have to search. In our very first guess, we get to eliminate a whopping 50 cells. So, wrapping up, often there's more than one way to achieve a particular computing goal. So again, it's compute because again, it's fundamentally a math or operation such as addition, subtraction, multiplication, and division. It's also important to realize that there's usually isn't a single data structure or algorithm that is perfect for every situation. For example, just because ordered arrays allow for binary search doesn't mean you should always use ordered arrays. In situations where you don't anticipate the need to search the data match, but instead to add data, standard arrays may be a better choice because their insertion is faster. So, another thing that I wasn't able to mention is that unordered arrays and binary search uh, goes hand in hand because for you to be able to search in the middle, the array needs to be ordered, right? Because that's the first steps that you need to do for you to be able to. So as you can see, you need to sort this first for unordered array. You need to order this. So for you to be able to use binary search, if you the main operations of your back end or your front end is about searching value, but let's say your primary operations in the front end of your application is insertion. So notice guys, for these complex interactions or softwares, the way we define operations is not through additions, subtraction, multiplication, and division. We define that in a more proper and easy to understand way, which is searching, insertion, and insertion. So as we discovered, for example, you're trying to add something like in a your for example a text field. You're trying to add, that's the main functions of your operation in the back end. For example, in a form, right? You're trying to add. Then a classic array is the best or better array. So because the insertion is faster, and the way to analyze competing algorithms is to count the numbers of steps each one takes. So those operations, again, the steps and then operations and different types of operations from those different or fundamental operations is what algorithm is. And big O notation, which we will discuss later, is a way for us to determine the steps uh, of those different operations for different cases. Now, yeah, oh yeah, oh yes, big O notation. This is the different way, the median, worst case, and best case that we discuss. But um, I think we will discuss this in the further videos because it's not that extensive here. So we're just gonna discuss the basic. The primary factor in determining an algorithm's efficiency is the number of steps it takes. We can simply label one algorithm a 22-step algorithm and another a 400-step algorithm because the number of steps an algorithm take cannot be pinned down to a single number. For a linear search, the number of steps search takes varies depending on the elements in the array. So the index could, or each index in the array could be named elements. I mean, another way to mention that sometimes is an elements. So the more effective way to measure is it is big O. So how many steps relative to n elements? So how many steps depending to the n elements of the array? Because remember, the computer can easily know how many elements are indexed in the array. So the way for us to usually measure that, or to make it measurement faster, is to get what already know, what's the fact that is known by the computer, which is the index or n elements. Big O achieves consistency by focusing on the number of steps an algorithm takes, but in a specific way. Let's start off by applying Big O to the algorithm of linear search. In a worst case scenario, linear search will take as many steps as there are elements in the array. For example, the value is at the end of the array. So that's the worst case scenario. But that's not the usual search value that is entered by the user. For n elements in the array, linear search can take up to n steps. The mathematical way to express this big O notation is ON. So it's ON, okay? So and then again, we measure the operations or the steps in operation using the worst case. Because if we are prepared for the worst case, then we can accommodate the best case and average case. Some pronounce this as big ON, other calls it order of n. My personal preference, however, is O of n. This is the answer to our key question. If there are n data elements, how many steps? So that the key questions we asked earlier is that how do we determine the time or efficiency of a data structure and algorithm? We don't determine time and efficiency. We determine the steps and the nuance of operations for each use cases, or the algorithms for each cases. Later we will get deeper or more detailed on the algorithm and how actually work in details using an actual code in JavaScript. The soul of Big O, there's actually more answer that it provides than our key question. So there's another questions than the efficiency and time that we need to ask, or the steps and operation. Let's say we have an algorithm that always takes 3 steps no matter how much data there is. So no matter how much the data structure does not matter, or the data on that data structure doesn't matter. That is for n elements. The algorithm always takes 3 steps. So before I continue, another thing to mention is that data structure is inherent to how our memory works. Like, you cannot boil down it to math. It's a new concept, therefore needs new vocabulary and thinking. So data structure is another way to describe memory. Okay, so our simplest or known way in computer science to discuss and understand how memory works. Okay, and the efficiency of our application, how fast it is to open up, will be determined by the algorithm or operations we used on that data structure using our code, our programming languages. So let's go back. So that is for n elements, the algorithm always takes 3 steps. So how would you express that in terms of big O? So this is another question. What if that no matter how much data structure you have, or data you have in the data structure in memory, it always get the operations 3 steps. Kinda like we're talking about the algorithm here. What if that algorithm always takes 3 steps? So based on what you know, it's O3. But as we will see, so an algorithm of the third kind, we can't describe binary search as being O1 because the number of steps increases as the data increases. So as the number of data increases in binary search, as we can see, took only 7 steps instead of 100. It also doesn't fit into the category of ON. since the number of steps is much fewer than the n data elements. So, uh, since we've defined the steps in binary search operations, so the way we describe the fundamental way to describe operation is through steps. So this binary search operation uh, can't be defined by that simple steps, because as the number of data that is put into that data structure in memory, as we can see, um, it doesn't define the binary search. It doesn't accurately express that. So how do we express that? How do we express that in terms of number of steps, which is the measurement? So the way it also doesn't fit into the category of ON, since the number of steps is much fewer than the n data elements, as we can see. So how do we do that? That's the issue. Binary search then seems to fall somewhere in between O1 and ON. So what is it? So of course, it could not take O0, without taking any steps. It needs to put some cognitive load, even if just one step, which is the most basic step. So in big O terms, we describe binary search as having a time complexity of O log n, or O log n. So time complexity is really, I would change, for me, in my opinion, for better understanding, I would change this as a step complexity, which is O log n. So how do we describe that operation? It's kind of like mystical or magic, because we only know addition, subtraction, multiplication, and division. So the way to actually do that is to describe this using O log n. So logarithms. So you knew logarithms in high school and high school and elementary maybe. The first thing to note that is the word logarithm has nothing to do with algorithm, even though the two words look and sound similar. Logarithms are the inverse of exponents. So exponents, like when, for example, 2, you raise it to 2, you multiply 2 by its same number. If you raise it to 3, you multiply the 2 by its same number by 3 times. 2 times 2 times 2. So for 2 raised to 2, 2 times 2 equals 4. 2 raised to 3, 2 times 2 is 4 times 2 is 8. Okay, so that's the inverse of that. So which is 8. Now the log base to 8, for example, if we put here O log sorry, now the log base 2, for example, the inverse 8 is 3. So if it took like if the n element, for example, is 100, if we measure that, for example, O log n of 100, so if we measure that in calculator, for example, for 8, the O log or the inverse exponents of 8, what is the inverse? It's 3. So it's only took 3 steps for an application for a binary search. So that's how we should measure, or the tool that we're gonna use to measure those type of operations. So O log n explained. So later we will explain why constants of base logarithm would not matter. So the base of that, whether it's 2, 3, does not really matter, though it matter just for the sake of simplicity here. But what matters is that it expressed as logarithmic, I mean inverse of exponent, which is faster than the linear steps. But for now, imagine the O log n as having base of 2, which is O log 2n. Now we can answer the key question. O log n means that for n data elements, the algorithm would take log 2n steps. If there are 8 elements, the algorithm would take 3 steps. Since log 2, 8 equals 3. Said another way, if we keep dividing the 8 elements in half, it would take us 3 steps until now. Practical example. So what this is the details that is what I'm saying that will allow us to how the software actually use that in details. The first thing to realize is that while it may not be fancy, any code that does anything at all is technically an algorithm. It uses an operation such as the basic math, addition, subtraction, multiplication, and division. It's a particular process for solving a problem, kind of like particular operations of the for solving a problem. So we're trying to determine if that operation that you use to solve a problem is actually the best way or the most efficient step, or the number of steps to get there. Now in this case, the problem is that we want to print all the items from a list. The algorithm we use to solve this problem is a for loop containing a console.log statement. To break this down, we need to analyze how many steps it took based on its algorithm and data structure, which we will discuss further in speeding up and optimizing code with Big O. We will also discuss different types of algorithm and data structures in different algorithms later. So here, because that's the how JavaScript create variables in memory. So if you want your application to took amount of variables, or here these things contains this array. So array is actually just it could be a combination of constants like this, or it could be more complex, such as combination of variables. So that's actually how your application talk to the computer. So that's actually how we program. Use CPU, copy the things that you download from your disk to the memory. This memory contains these little details of data structure, which is in this case classic array and variables. So how do we create this variables, or sorry, it's not variable, kind of like a variable, fundamentally no, it's not a variable because it could also contain just constant, but it's highly related to a variable, as we will see in the later videos. So let things equals to apples, baboon, scribs, dulcimers. For constant thing of things, console.log, here's a thing, and then $sign thing. So this thing we we insert that in a console log statement. So the algorithm we use to solve this problem is a for loop containing a console.log statement. So we use a binary search here. Sorry, since we want to print all items here, the very act of printing it in our memory into our LCD or on the pixel is actually for this list of this constant. So these are another way to mention this is list, or to view it list. For us to list this and then put in the console.log in our LCD is uh, uh, an algorithm itself. Even just using a simple for loop to get all these values from our index or from our computer is an algorithm itself. So wrapping up with big O notation, we have consistent system that will allow us to compare any two algorithms. With it, we'll be able to examine real life scenarios and choose between competing data structures and algorithm to make our code faster and able to handle heavier loads. Heavier loads like compute operations done using our application. So so this O login and then ON is a tool, a steps tool, a concept, an idea that we used for us to organize, our thinking about how this memory CPU actually work, or computer, for us to be able to better create a code. It's an exact science that if you um, inhale and took it to heart, will be able to help you create faster code and compare competing data structure and algorithm in codes. Speeding up your code with Big O. Big O notation is a great tool for expressing the efficiency of an algorithm. We use it to quantify the difference between binary search versus linear search. As binary search is O log n, a much faster algorithm than linear search, which is ON. But it still depends on the operation. For the normal operation, if for search operations, definitely binary search is faster than linear search. With big O, you also have, so because these two operation is in the same operation, like for a classic array, let's say you're trying to insert, you're not trying to really search something, then inserting operation is much faster. So I just want to clarify that. It's just that this operation it's the same operation. It's still search operation. So with big O, you also have the opportunity to compare your algorithms to general algorithms out there in the world. And you can say to yourself, is this a fast or slow algorithm? As far as algorithms generally go, if you find that Big O labels your algorithm as slow one, you can now take a step back and try to figure out if there's a way to optimize by trying to get it fall under a faster category of Big O. So the way or the tool we use for speeding up our code using Big O is that by looking at how it plays or falls in ON or O log n. If you know that it's on ON, then you can now push that in the O log n if it's possible. Now, bubble sort. Before jumping into our practical problems, though, we need to first look at a new category of algorithmic efficiency in the world of Big O. To demonstrate it, we'll get to use one of the classic algorithms of computer science lore. So there is actually another tool that we can use to measure this operation or the efficiency of algorithm. To demonstrate it, just as we demonstrate an ordered array using a binary a binary search using an ordered array and ordered array as a binary search. We're gonna demonstrate it using a classic algorithm in computer science, which is the sorting algorithm. As you can see, guys, another thing about this, kind of like a sentence, it's hard to understand this through one concept, such as ordered array, because you cannot understand ordered array without first understanding the binary search. I mean, without understanding both at the same time. Kind of like a sentence, word doesn't have its meaning without the combination, a specific combination and sequence of that word produce its meaning. So it's the same thing with this. So if you ever wonder why is it that it's hard to understand the operations such as binary, the steps, the different kind of operation, insertion, searching, um, deletion, shifting, swapping, comparison. Why is it hard to understand that just alone? Because you need to understand it as a whole that produce its meaning. Kind of like a word itself doesn't have that meaning. Could have like million meanings, but if you really don't put that into a use case or a context that will help it make it that will make it useful and provide this magic meaning, then you would not be able to use the concept, right? That's the reason why we're trying to define this concept, for us to be able to use that in the back of our mind unconsciously while we're creating our code. So let's go back. Sorting algorithms have been the subject of extensive research in computer science, and tens of such algorithms have been developed over the years. So more than 10 of sorting algorithms have been developed, and the most commonly used in computer science. They all solve the following problem. Given an array of unsorted values, how can we sort them so that they end up in ascending order? So again, because the memory, the structure of how memory works, you can only I think memory is another metaphor, is how you read as a child. So if you read like a lot of books, you will have a lot of memory to store and to to be able to understand at the same time, kind of like keep all the index, right? So the memory, or given an array, so kind of like memory is almost synonymous to an array, right? Because sets is an array as well, but it's just remove the duplicates, but it's still an array. Like fundamentally, it's an array. How many values you could store in that array or in that memory? So this sorting algorithm, you could have a lot of memory, but if you could not use that, if you could not source, because the algorithm is still important in the memory, right? Or the software that you use. So like kind of like in the book, right? You may have a lot of books, but if it's not a good book, then it's not a good algorithm, because you will not be able to use the right uh, the right book at the right time. You didn't read the right books that will fit the way your hardware are designed, or the way your life, your environment are structured. For example, if you're in the Philippines and you're reading like um, Western books or other unrelated books, it's not the right book or algorithm, and you only have a limited amount of time before you get into 25 years old as a person, right? So you need to use those widely. Only use the books that you know has the right algorithm. So I think that's a good metaphor in this as well. So the given an array, how can we sort them that they end up in ascending order? In this chapter, those following uh, we're going to encounter a number of these sorting algorithms. Some of the first one you'll learn about are known as simple sorts. So in this, all of the subsequent videos we're gonna discover is about different types of this algorithm, in that they are easy to understand but are not as efficient. So simple sorts that sort the ascending could be simple to understand but are not as efficient. So that's a bubble sort. So there's a simple sort, right? That's a bubble, what we call bubble sort. They may be easy to understand, like yes, we can make this ascending, or we can sort this data in the memory in ascending order. It's simple, it's easy to understand, but it's not efficient because it took you like O n steps, when there could be O log n steps. So bubble sort in action. Assume you want to sort the array 42713. It's currently out of order, and we want to produce an array that contains the same values in ascending order. So let's say your application wants to ascend the data. For example, in his e-commerce app, he wants to ascend it using the least price to higher price. This is the application for that. First, we compare the 4 and the 2. Step 2, they're out of order, so we swap them. Next, we compare the 4 and 7. So as you can see, we are using a swap operation here. We're not searching, we're using another kind of operations. The efficiency of bubble sort. So the bubble sort algorithm, or the bubble sort swapping operations, contains two significant kinds of steps: comparisons and swap. So another thing that the new ones, as you can see, there's already also a compare and swaps. So as you can see, there is two operations that we took. So it's kind of like more complex if you would think about it in just like a normal reading. We just take one step for the computer, and kind of like in a way in more complicated and more have additional steps than searching, right? The comparisons compared two numbers with one another to determine which one is greater. Another thing is that actually the searching, but I mean there's different types of searching. For linear search, kind of like more complicated than just a simple linear search, right? A binary search, of course, is a faster type of linear search, but this kind of like more complicated because it has comparisons and swaps. So the comparison compared two numbers with one another to determine which one is greater, and swaps from the word itself with one another to sort them. So what it does is this: the comparison compared two values. In this case, it's number with one another to determine which one is greater, and swaps from the word itself. Swap with one another to sort them. So as you can see, if we apply this in code, we're gonna use a less than operation to compare. If less is something like that, which we're gonna discuss later. Let's first see how many comparison steps we took. In our first fast, we had to make 4 comparisons between sets of 2 numbers. So here we need to compare 2 and then 4, but there's just a first pass 4 comparisons. So there's 4 comparison steps between sets of 2 numbers, so that's 4 steps. In seconds, again, that operation took 4 comparisons, right? So those has kind of like, yeah, it kind of like have 4 steps. In second, we only had to make 3 comparisons because we didn't have to compare the final 2 numbers, since we knew that the final number was in the correct spot due to the first pass through. In third pass, we made 2 comparison sets. So how many steps did we took? 4, 3, and 2. So one of the recurring theme here is that for the last value in the index, we wouldn't need to go through another pass because we know that the final number was in the correct pass, which we're gonna later see. A quadratic problem. Now we can replace a slow ON2 algorithm with a speedy ON1. So this, as you can see, a bubble sort. So a simple algorithm, easy to understand but is inefficient, is actually took a lot of steps. And for linear search, it will be easier for us to do this. For reading, for other operations, it will be easy. Here we did how many steps? Comparisons 4, 3, 2, 4, 5, 6, 7, 8, 9. It took us 9 steps. So a quadratic. So how can we replace that 9-step algorithm with the speedy ON1? So let's say you're working on an application that analyzes the rating people give to products, where users leave ratings from 0 to 10, and you're tasked to write a function that checks whether an array of ratings contains any duplicate numbers and will be used in more complex applications in other parts of the software. For example, so you're tasked to write a function. So this function is actually the operation. It's just an operation that you were trying to create, a combination of this programming syntaxes to create a function that will allow you to solve this issue. It's a set of instruction. From the word itself, an algorithm is just a set of instruction that allow us to complete a certain task. So whether an array of ratings contains any duplicate numbers and will be used in a more complex. So what comes to mind is the set array, right? So for example, the array 153914 has 2 instances of number 1. So we'd return true to indicate that the array has a case of duplicate numbers. So let's say this has a 2 instance of 1 number in its array. So we'd return true to indicate that the array has a case of duplicate numbers. So we compare that first, right? So those are the basic operation that we use in if-else statements, by the way, in this code. And also we use so you can see the naming has duplicate value. It's we use the name for the function or the algorithm based on the task we are given to, like has duplicate value, and we're gonna use compare and swap. So in this case, we're gonna use the compare operation. We're trying to gonna apply that in the JavaScript programming language. So a linear solution. So here we have a function, and then we have a for loop inside that function. What follows is another implementation of the has duplicate function that doesn't rely on nested loops. which is more efficient than the previous one. So as you can see here, they don't have nested loops. Okay, because for nested loops, there is actually an efficiency, because sometimes the loop goes on to those all of the index when it doesn't have to, and then the inside loop as well, and then it needs to go that until the loop ends. So here you create a function, and then inside the function you create existing numbers, uh, and then you have for loop inside it, and then you have this if statements that actually compare if it's equal to you know this is how we write code. If it's equal to 1, return true, else existing number array I equals to 1, and then return false. So we use if for and then if else statement within the for. First, we create an array called existing arrays, which start out empty. Then we use a loop to check each number in the input array. So the existing numbers that we use as a content start as empty. Then we use a loop to check each number in the input array. So in this loop, check each number in the inputted array on our application. So usually our application will ask that, right, using a text field or a text box that provides those options. It could be a string as well, but the key thing is that we're gonna remove the duplicate. As it encounters each number, it places an arbitrary value. We've chosen to use a 1 into existing numbers at the index that is equal to the number we're encountering. For example, let's say our output is 358. When we encounter the 3, we place 1 at index 3 of existing number. So existing array will now be the rough equivalent of this. 0, 0, 0, 1. As you can see, it's in the third index. There's now a 1 at index 3 of existing numbers to indicate. And remember, for the future, that we've already encountered a 3 in our given array. So what we actually do is we create an empty array with this, and then we put that in here, a 1 on that to mark it. So this is what it meant. So when our loop then encounters the 5, there's now 1 at 3 of index array numbers to indicate. And remember, for the future, that we've already encountered the 3 in our given array. When our loop then encounters the 5 from the given array, it adds 1 to index 5 of existing numbers. So these are the input array 3, 5, 8. It is kind of like the index, and then finally when we reach the 8 existing numbers will now look like this, which, as you know, we're just using the indexes of existing numbers to remember which number from the array we've seen so far. Now here's the real trick. Before the code stores a 1 in the appropriate index, it first checks to see whether that index already has 1 as its value. If it does, this means we've already encountered that number, meaning we found a duplicate. So that's the magic of that, because if there's already a 1 on this array that we use using this for and then if else, it means it found a duplicate. So that's the linear solution for finding a duplicate value. But a duplicate or a set array will definitely more efficient, could be more efficient. I mean, yeah, it definitely is more efficient than this because the array itself does not allow that duplicate value. If this is the case, we simply return true and cut the function short. So if this is the true, we will cut the function because we don't need to add or mark that one if it doesn't have a duplicate yet, or I mean, if it doesn't have, I mean, those would not help us determine if there's a duplicate if we're gonna add a one again. That's why we end that function return false. If we get to the end of the loop without having returned true, it means that there are no duplicates and we return false. So we cut the function here, and then if we get into that end of the loop of that empty array we created, we return false. To determine the efficiency of this new algorithm in terms of big O, we once again need to determine the number of steps the algorithm takes in worst case scenario. So again, to determine the steps, we need to know the worst case scenario because it will happen. Here, the significant type of step is looking at each number and checking whether the value of its index in existing number is a 1. So the significant type of operation here is looking at each number and checking whether the value of its index in existing number is a 1. So what is that? Looking at each value. So it's a linear, right? And then another operation for that is comparison. Like in index in existing numbers is a 1. If existing numbers array I equals to 1. So that's a significant part of the step in our code. In addition to the comparisons, we also make insertions into the existing number arrays. So aside from linear search and comparisons, we also make another operations. We took another steps, which is insertion in the existing numbers array. But we're considering that the kind of step trivial in this analysis. So since this insertion is just one step, it doesn't really amount to compare to the searching and comparison steps. More on that later on the next videos. Now in terms of worst case scenario, such an scenario would occur when the array contains no duplicates. Why is this worst case scenario? Because you have to go to its index and then just to find out that there's no duplicate. So that's how you measure the efficiency or the steps that it will took in which our function must complete the entire loop. These new algorithms appear to make n comparisons for n data elements. This is because there only one loop and it simply iterates for as many numbers as there in the array. So it's just one loop because again we need to discard the n steps. So linear search and then comparison on each index. So in each index you compare it, and then so that's the significant step. So how do we express that? How do we measure that in terms of mathematical operation? We can test out this theory by tracking the steps in the JavaScript console. So here function has duplicate value array, let steps equals to 0, cost and existing number equals to empty. For let I equals to 0, I is less than array I plus 1, steps plus equals to 1. So we create it's actually a variable that will add 1 as we loop in this parent loop. Now if we create a if else statement in this parent loop, existing numbers I is equals to 1 returns true. So we will go to the next index if there's already a 1, else existing number array I equals to 1. So that existing number, we will add it to 1. Otherwise, we will console log the steps and then we will return false. If we run has duplicate value 14529, now we'll see that output in the JavaScript console is 5. So if we input on our front end or our LCD 14529, it will output in the JavaScript console 5 because it took us 5 steps to find a duplicate, which is the same as the size of our array. We'd find this to be true across array of all sizes. The algorithm then is ON. We know that ON is much faster than ON2. So ON2 is not efficient as the ON. So now we have 3 tools, ON2, OLogN, and ON. By using the second graph, we've optimized. So by using our this second approach, we've optimized our has duplicate value function significantly. This is a huge speed boost. So again, on that operations, first we're trying to determine steps, but on that step we're trying to determine operations. Those operations as nuance operations, and then those nuance operations could provide more nuance and complex things like this, which create an entire algorithm itself. In this case, a linear solution for determining the duplicate value. So yep, so by using this second approach, we've optimized our has duplicate value function significantly. This is a huge speed boost. One disadvantage with this implementation is that this approach will consume more memory than the first approach. So here we have the first approach actually consume less memory, and this actually consume more memory because you have this you have to track all of the index all at once. So I wanna go back and further discuss the ON2. So this so as we can see, bubble sort, took us from this 1, 2, 3, 4, 5 ON2 speed compared to just ON. So we use a linear solution to find the duplicate, an algorithm. We created a linear solution for an algorithm to make those ON2 more efficient. Let's try to search this instead. I couldn't find the O log N2, which is just more slower than ON. So here we have 2 comparison, plus 3, that's 5, plus 4, sorry, let's see how many comparison. 4 comparison. Oh, I see. So bubble sort. So for bubble sort, since we need to compare and swap, as you can see, first we compare the 4 and 2. So let's first, how many comparison tests we take in our first pass? We had to make 4 comparison, and then between 2 sets of number, and then on the second pass we had to make 3. So these are the ON2, the bubble sort. So that's the ON2 actually, because we need to swap. So as you can see, 1 2 3 4 5, it has 5 index, but it took like 9 comparison. And then how many swap is this? And then we swap like almost 10. Sorry, to we swap this here, 2 4, and then 1. Yeah, so it's multiplied by 2. The linear, or the number of array, was multiplied by 2. So we used an algorithm. A linear solution has duplicate value that check it is there's a duplicate. So as you can see, we can use these operations, a combination of these operations. In this case, the operations that we use is looking at each number, which is linear search, and then checking whether the value of, we're still looking at each number, which is searching, and then we're still comparing these, but what's efficient here is that we store it in the memory first, and we use that memory. That's why it took more memory than the previous one. So we use that one in each index to compare if there's already existing value like that. That's why it makes us ON steps. So it's clear that having a solid understanding of big O can enable you to identify slow code and select the faster of 2 competing algorithms. However, in some situations, big O notation will have us believe that 2 algorithms have the same speed, while one is actually faster. In the next chapter, you're going to learn how to evaluate the efficiencies of various algorithms, even when big O isn't nuanced enough to do so. So as you can see, it's kind of like nuance. It's really not easy to understand that, because we have to combine all of those concepts. The ON2, the O log N, and the ON are all interconnected. So optimizing code with another question now that we're trying to answer is that, what if 2 algorithms would have us believe that they have the same speed? What are the techniques that we're gonna use? Of course, we have to demonstrate this with an example as well, uh, using a selection sort algorithm. Now, previously, we explored sorting algorithm known as bubble sort. So those are the first type that sorting algorithm we discussed, which had an efficiency of O(n)(2). We're now going to dig into another sorting algorithm called selection sort and see how it measures two bubble sort. Now we check each cell of the array from left to right to determine which value is least. As we move from cell to cell, we keep track of the lowest value we've encountered so far. We'll do this by storing its index in a variable. So since we're still trying to sort things, we need to check each of the array from left to right to determine which value is least. As we move from cell to cell, we keep track of the lowest we've encountered so far. We'll do this by storing its index in a variable. So we keep track, we compare that, of course, in the variable. We're going to use a comparison operation. If we encounter a cell that contains a value that is even lower than one in our variables, we replace it so that the variable now points to the new index. So again, if we encounter a cell that contains a value that is even lower than the one in our variable, we replace it so that the variable now points to the new index, so that those lower that variable now points to that new index. It is now on the beginning index, because again, we're trying to sort things in this sorting algorithm. One of the key things to understand here is that those basic operations, we're trying to minimize that by offloading that to our memory of our computer, by storing it in a variable. So this is what algorithm does. It minimizes those steps that would take. So that's you can see how that algorithm makes things, the choice of algorithm makes things faster, depending on how we chose it. What algorithm we chose in what context. So here, lowest value so far is 4, which is at index 0. Once we've determined which index contains the selection sort in action, here's an implementation of sort via pass-through. Started from I for the index and subsequently use j to keep the lowest value and index. Oh my god, why can't I? So let's say it's I, guys. So started from I for the index because it's I here. So function, we created the selection sort function with this array. So we have a for loop, and we let lowest number variable equals to I, and then we use j to keep the lowest value and the index as well. So to track or to track the lowest value and the index, because this is the child for loop. So if array j is less than array lowest number index, lowest number index is equals to j. So this the purpose of this j or child for loop is to keep track of the lowest value and the index. So it offloads this operation in the memory to keep the number of steps as low as possible. Now after if of that, if lowest number is not equals to I, array I, and then array lowest number index is equals to array lowest number and then array I, and then close and then return array. So these are our logic or the operations that we're gonna use in the backend. Now we set things up by inspecting the value at index 0 first. By definition, it's the lowest value in the array we've encountered so far, as it's the only value we've encountered so far. So we keep track of it. It's in a index in a variable. Now lowest value so far is 4, which is at index 0. So we compare the two with the lowest value so far, which happens to be 4. So since this j keep the lowest value in the index, that's where we compare this. So initially this j has 4, and then since we get a new value from the first step, so these are the first step, we compare the two with the lowest value that we keep track, in the I first, which happens to be 4. The 2 is even less than 4, so it becomes the lowest value so far on the 2. So now the J4 loop has the 2 and the index you're now keeping track of, which you're now in the first index. Then step 2. So as you can see, in that one step, we got a lot because we have two codes of this for loop. So instead of uploading the step on the basic operations or in the data structure, we use an algorithm to offload it into memory. Now step 2, we compare the next value, the 7, with the lowest value so far, which is 2. The 7 is greater than 2, so 2 remains our lowest value, so nothing will happen. Now step 3, so we have now 2, 4, 7, 1, 3. We compare the 1 with the lowest value, which is this one so far. Because the 1 is even less than 2, it becomes our new lowest value. So the j keep tracks of that index where the lowest value and the 1, which is in the 0. We compare the 3 to the lowest value so far, which is the 1. And we reach the end of the array in just step 4. And we've determined that 1 is the lowest value of the entire array. Because 1 is the lowest value, we swap it with whatever value is at index 0. The index we began this pass through. So here, we passed it in step 5. So another step is swap. Since we've moved up, again, so we used to compare to measure the step using just the basic operation, no matter what algorithm inside those basic operation we've mentioned, such as for searching, we could have linear search, binary search algorithm, or for what you call this, for the bubble sort, we use comparison and swap test, which has ON2, and for linear solution of this algorithm or has duplicate value, it has OLAG and step. So no matter what it does, comparison, shifting, swapping, it's just a one step, we use just one step to compare that. Now since we move the lowest value to the beginning of the array, that means the lowest value is now in its correct spot. We're now ready to begin a second pass through. So we've those pass through for the loop are actually are able to sort this array. So this is the array in the first pass through. The first cell, index 0, is already sorted, so this pass through begin at the next cell, which is index 1. The value at index 1 is the number 2, and it's the lowest value we've encountered in this pass through so far. We compare the 7 with the lowest value so far. The 2 is less than 7, so 2 remains our lowest value. We compare the 4 with the lowest value so far. The 2 is less than 4, so 2 remains our lowest value. Step 8, we compare the 3 with the lowest value so far. The 2 is less than 3, so 2 remains the lowest value. We've reached the end of the array. Since the lowest value from this pass-through was already in its correct spot, we don't need to perform a swap. This ends our second pass-through, leaving us with this 1, 2, 7, 4. As you can see, 7 are still. Now we begin with the third pass-through. Setup, we begin at index 2, which contains the value 7. So this is the third pass-through in the for loop. The 7 is the lowest value we encountered so far in this pass-through. So another thing to notice is that the reason why algorithm and this code in the backend seems magic, because it all does this in its hardware so fast that it seems magic, but it's just like doing this in the backend, this computation. We compare the 4 with the 7. Step 9, we note that 4 is our lowest new lowest value. Now we encounter the 3, which is even lower than 4. The 3 becomes our new lowest value because we keep track on the last index on J, and this is the third fast loop. We know that we can only this lowest number index. This is the only thing that we need to switch. What's the next lowest value? So step 11, we'd reach the end of the array, so we swap the 3 with the value we started our pass through with, which is 7. So here we switch the 3. We know the 3 is in the correct place within the array. So now we're gonna move on to the next index, which is 0, 1, 2, third index. Well, you and I can both see the entire array is correctly sorted at this point. The computer doesn't know, so it needs to add another step. So it needs to begin a fourth pass-through. Set up, we begin the pass-through with the index 3. The 4 is the lowest value so far. Step 12, we compare the 7 with the 4. Lowest value equal 4. So last step is a comparison with 7 and 4. Because we start here and we know that it's already sorted, we will start with the 0, 1, 2, 3, 0, 1, 2, 3, third index, and then the 4 remains the lowest value we encountered in this part so far, so we don't need to swap it since it's already in the correct place, because all the cells besides the last one are correctly sorted. That must mean this last cell is also the correct order, and our entire array is properly sorted. So that's the selection sort in action. Now we began our code with a for loop that represent all this pass through until the second to the last value. It doesn't need to represent the pass through to the second to the last value because it will be fully sorted at that point. That's why we have this for let I equals to 0, I less than array.length minus 1. So we only loop on the array.length minus 1. So these are the characteristics of sorting algorithm. Again, we're offloading this to memory, these steps. Now, next we began tracking this, and later we will, in the next videos, we will discuss what is the ON, or the mathematical expression for this. Next, we began tracking this, the index that contain the last value. Next, we began tracking the index that contains the last value. After since we know that for sorting algorithm that we're not gonna go to the last, we track that the index that contain the last value, which is lowest number index I. So this lowest number index will be 0 at the beginning of the first pass through, 1 at the beginning of the second, and so on. The reason we keep tracks of index is because we want to simultaneously keep track of index and value itself. So the reason is we need to keep track of the index and value because we need to access to both the lowest value and its index in the rest of our code so that we can reference both. We can check the lowest value by calling array lowest number index. So since we let that I, lowest number index, we can call that on our code, so we can start from there in our loop. Within the pass-through for loop, we compare the remaining values of the array to see if they might be a lower value than the current lowest value. So since we check that, we keep track on that lower value. We keep check inside the array, which is loop another again for the for loop. Kind of like here. First, you start there and you keep track of this one, and then after that, you keep track with the another for loop here to check, to compare if it is greater or lower than the one you keep track first. So yeah, we get for let j equals to I plus 1 because we want to add 1 to that index. So this I is an index. If j is less than array.length, j plus equals 1. If we find a lower value, we'll store this to the lowest number index. So if we found that lower value, we store that again. If array j is less than array lowest number index, so we keep the lowest number index as the if array is less than the array lowest number index, then lowest number index will be j, the new j. So by the end of this loop, inner loop pass through for loop, we'll find the index of the lower value in each pass through. If the lowest value from the inner loop for loop compare and store is already in its correct place, which would happen when the lowest value is the first value, we don't need to do anything. But if it's not in the correct place, we need to perform swap to the value I. So if it's not, we were gonna swap the j to I, which was the index we started from the parent pass through for loop with. If lowest number index I equals to I, array I is not equals to I, array I equals to array number index equals to array lowest number index, then array I. Finally, we return the sorted array to provide to the console later. So we will discuss further the efficiency of selection sort, ignoring constants, which we will now discuss why those base constants don't matter, and big O categories, the worst case, best case, average case, practical example, significant step, and wrapping up. And then optimizing for optimistic scenario, which is best case, insertion sort. So we will discuss this algorithm as well. Insertion sort in action, the efficiency of insertion sort, the average case, a practical example, big O in everyday code, mean average of even numbers, word builder, array sample, average Celsius reading, clothing labels, count the ones, palindrome checker, get all the products, password checker, wrapping up. Blazing fast lookup with hash table, hashing with hash function, building a thesaurus for fun and profit, but mainly profit, hash table lookup, dealing with collisions, making an efficient hash table for organization, hash table for speed. So we will discuss all of this missing concept in the later video. And again guys, thank you for watching. See you on the next video.